So make sure before you watch this video that you actively work the review on your own. Okay, that will give you a lot more practice than if you just watch me do the questions. The point of the review is for you to practice questions like you will see on the test. Okay, so let's start with number 1. So the first thing we did at the beginning of the semester was limits. And remember, we had limits where x, or in this case t, is approaching a number, and we had 3 methods for that. We either try the plug-in method, or we try to simplify, or we might try a table. So notice for this one, there's no problem with us just plugging in 3 everywhere there's a t, and use your calculator and you'll just get 29 for an answer. Okay, so your plug-in method should be your first option. All right, so let's look at this one. Number 2. Okay, notice if you use the plug-in method for this problem, you're going to get 0 in the denominator. Okay, so I'm just going to write this. Plug-in method doesn't work. The plug-in method actually gives you something you're not allowed to have. It gives you 0 over 0. Okay, so that means you try something else. You don't leave it as 0 over 0. You don't say the limit doesn't exist. You try something else. So this factors into x minus 3, x plus 2. On the bottom, it factors into x plus 2, x minus 1. And notice I have some common factors here, right? So I could cancel out the x plus 2's, and then I'm left with the limit as x approaches negative 2 of x minus 3 over x minus 1. And then notice now we can plug in with no problems. So now we're going to plug in x equals negative 2, and we're going to get negative 2 minus 3 over negative 2 minus 1, negative 5 over negative 3, which is just 5/3. Okay, so notice my process. I tried the plug-in method. It was a no-go, so I tried something else. All right, so make sure you know the difference between limit problems where x is going to a number versus when x is going to infinity. Our process for solving those are completely different. Okay, so remember, the process for solving problems where x goes to infinity is you put everything over the highest power of x you have in the denominator. This is only for, again, problems where x is going to infinity. So I'm going to put all the terms over x cubed, since that's the largest power I have in the denominator. So that's going to leave me with the limit as x approaches infinity of, now we're going to simplify. Okay, so that would be 1 over x. Here we would hit 4 over x squared, and then on the bottom we'll get 2. Make sure you simplify correctly. And then because x is getting extremely large, any of these fractions where we have a number over x to a power are all going to get close to 0. So in the end, you just get 0 over 2, which is a limit of 0. I included a problem on the review where the limit was 0 because just to showcase that 0 on the top is fine. It's 0 on the bottom that we're worried about. So make sure you know the difference there. All right, so let's do one more. Remember that if you get a problem where the limit is going to negative infinity instead of infinity, your process is exactly the same. You will still put everything over the highest power you have in the denominator. So we're going to get 2x over x plus 3 over x. On the bottom, we'll get x over itself minus 2 over x. Okay, remember what I said when we first learned this. One of the most important steps is the simplification step. So 2x over x is 2. 3 over x doesn't simplify. X over itself is 1. And 2 over x doesn't simplify. So in the end, we end up getting this to go to 0. And also this, right, since they are numbers over x to a power. And so we end up getting just a plain old limit of 2. Okay. Remember, on all 4 of these limit problems, you also could look at a graphing calculator and see kind of what the graph is doing at that particular location. Okay. All right, so speaking of graphs, if you look at number 5, so I'm going to kind of put the graph up here. So here's the graph for number 5. The question is, what's the limit as x approaches 2? So let's look at this picture. As x approaches 2, notice, or sorry, negative 2, notice there is no plus or minus after it, so that assumes that we're going to come from both directions. So notice my fingers here. We're squeezing in on negative 2 from both directions, and we're being asked what's the y value getting close to as we do that. And notice there's not really a whole lot of work to show. We would just say the limit as x approaches negative 2 of this function. If we approach from both the left and the right, we're getting close to a y value of 3. Okay, so not a whole lot of work to show for that one. All right, let's look at number 6. Number 6 is another visual problem. So I'm going to kind of put it off to the side and see if we can kind of write it as we go. So the first thing is, what is the limit as x approaches a from the right? Okay, so as we approach a from the right, notice we're traveling along this curve and we're going up sharply. So we would say the limit is infinity. Okay, you can also say it doesn't exist, but I at least want to see infinity for this problem. Okay, so the limit as x approaches a from the left. So if we approach a from the left side, notice we're going down forever, so that limit is negative infinity. Again, these limits won't exist since if the limit is infinity, the limit doesn't exist, but I still want you to indicate that you understand whether it was going up or down. But notice the third question is asking, is there an overall limit? And notice one direction we go up, one direction we go down, so this one would be a true does not exist. Okay, part D, the limit as x approaches infinity of g of x. So notice this is asking the limit as we go to the right. So as we go to the right, y gets closer and closer to 0, so that's the limit. Okay, so part E, where is the graph discontinuous? Remember the prefix dis means not. So it is discontinuous at x equals a. All right, so let's finish this one off. Identify the intervals where g of x is continuous. Okay, so if it's not continuous at a, it would be continuous everywhere else. So the interval notation would look like this. Now, probably on the test, I would actually give a number here instead of the letter A, but it's the process that I want you to know how to do. And then the last question, is g of x differentiable at x equals 2, y or y not? Remember, differentiable means we can find the derivative, okay? And so the answer is no, we can't. And that is because the limit is not defined here. But honestly, also because f of a is undefined as well. In other words, f of a doesn't exist. Okay, so differentiable means, are we able to find a derivative, yes or no? Okay, so clearly that's a no on that one. Okay, number 7. Identify where the function is continuous. So for number 7, I'm just going to write this. F of x is a polynomial. If you can tell for sure that it's a polynomial, then it's continuous everywhere. There's no work to show. There's no real discussion. It's just continuous everywhere if it's a polynomial. More interesting is 8 and 9. So it's only going to be continuous as long as the denominator is not 0. Okay, so we need to find out when the denominator would be 0. Okay, so notice we need to factor this. By the way, if you look back at number 2, we already factored this quadratic, and this is what we got. So we got x equals -2 and x equals 1. Okay, these are where x is discontinuous. Right, so we want to kick those numbers out, in other words. So I showed you this before and I told you it was optional. But if you have negative 2 and you have 1, we don't want negative 2, we don't want 1. So it's everything to the left, in between, and to the right. So the final answer is that it's continuous for negative infinity, but stop at negative 2. From negative 2 to 1, not including 1. And then finally from 1 to infinity. Okay, notice we would use parentheses because we definitely don't want to include this negative 2 in this 1. Okay, so let's look at number 9. I think it's our last continuous problem. So h of x equals 2 over 3x squared plus 1. So notice we would set this equal to 0 to try to find out where the bottom is going to be 0. Okay, but if we solve here, maybe you will see it pretty quickly. But notice if we do our algebra here, we're going to say x squared equals negative 1/3. And then when I go to take the square root of both sides, which is what I would try to do to find x, notice I'm going to get imaginary solutions. I actually don't even need to go further. Okay, so what this means is nothing makes the bottom 0, so I'm going to say no real number makes the denominator 0. Okay, so what that means is there's actually no restrictions at all because there's no way the bottom can ever be 0. So that means it's continuous everywhere. That is the worst infinity symbol ever, but there it is. Okay. So the point is we're trying to find out where, what would make the denominator 0 so we can kick those numbers out. And notice in this case we didn't have any numbers to kick out, which means it's just continuous everywhere. Okay, number 10, it says give a pair of limit expressions that describe the end behavior. So this is what the graph is doing at the far right and at the far left. So all this is you just take whatever the equation is and you're going to do one of two things. You're going to do the limit as x approaches infinity and as x approaches negative infinity. Okay, just know that this one is the far right because we're going to positive infinity, and this one is the far left. But notice if we plug in, not really plug in, but if we think about the largest positive number we could possibly think and we look at the highest power, notice that if we plug in, say, 10 million or something really large, since x is going to infinity, we're going to get an even larger negative number because of this negative sign. So this is just going to be negative infinity. Okay. Notice if we plug in a very big negative number, we're going to have the negatives kind of cancel each other out. So think of like negative 10 million. If you cube it, it's going to be negative, a huge number, right? But then it's going to cancel out with this negative number. So this is going to be infinity. So to be honest, you really just kind of look at this highest power term to kind of determine what would happen with the sign. The question is whether it was positive or negative infinity for number 10. For number 11, the question is different. So again, though, we need to say the limit as x approaches infinity of x squared minus x minus 12 over 2x squared plus 5x minus 12. Okay, so I'm looking at my key. I do need to change my key. It looks like I changed this question a little bit. Oh, no, I didn't. I'm just writing down the wrong question. Well, there you go. I was thinking my key was wrong. Sorry about that. So let me actually write down number 11. That would be helpful, right? Okay, so what I'm not going to do is show this process. If you go back and look at question number 3 and 4, it would tell you the process for this. You would put everything over the highest power in the denominator. But if you do that, so I'm just going to say show work here. I don't think I need to show that process again. Okay, but the answer would be 9/4. And by the way, the process is the same to show the negative infinity version which means you're actually going to get the same thing again. So if you were solving this, you wouldn't need to show the work twice. Okay, you're going to get 9/4 for both of them. So by the way, what this means is there's an asymptote at 9/4. Okay, this means as we go to the right up on number 10, as we go to the right, y goes down sharply. As we go to the left, y goes up sharply. That's what that means. But these are both approaching a value, which makes it an asymptote. All right, so speaking of asymptotes, now that I have the right question, that would be helpful. Okay, so remember for asymptotes, for vertical asymptotes, after you've done simplified, you've done simplified. After you are done simplifying, then you would set the denominator equal to 0. There is no simplification that we can do here, so you would just set that equal to 0. So notice that the bottom would be 0 when x is -2 and when x is 2. Okay, but as far as the vertical asymptotes go, we would just say x equals -2 and x equals 2. So not to be confusing, but here I was just saying what x would not be allowed to be, and it's not allowed to be them because there is asymptotes there. Okay, for the horizontal asymptote, there is a little bit more work. Okay, so for the horizontal asymptote, you have to do the end behavior, the limit as x approaches infinity of x over x squared minus 4. Again, I've already shown you the process here, so I don't want to show it again. But if you do the process, you're going to get 0. So again, I'm going to give you a little note here. You need to show your work here. But you would just put everything over the highest power of x. Okay, but you would end up getting 0, and notice that if you do the negative side, you get the same thing. So I'm going to mention it, but honestly, I wouldn't have to really show it here. So what that means is that there's a horizontal asymptote at y equals 0, because we got 0 for both of these. Okay, so let's look at number 13. So f of x equals x squared minus x minus 12 over 2x squared plus 5x minus 12. So if you factor the denominator, you would need to factor both top and bottom just to make sure there was no simplifications that could be made. So the top factors into this, right? The bottom factors into 2x minus 3 times x plus 4. Now, if there were some simplifications to be made, you would do those, but notice in this one we don't have any. So for this one, we would just set each of these equal to 0. So the vertical asymptote will be x equals 3/2, and also x equals -4 if you set both of those equal to 0. For the horizontal asymptote, remember this is where you find the limit as x approaches infinity. And so what's the highest power in the denominator? It's x squared. So if you put everything over x squared and you do all your process, you're going to get 1/2. Okay, so again, I'm going to say show work here. Just for time reasons, I'm not going to show every little step because we've already shown that in example 3 and 4. So I'm just going to say see example 3 and 4, or number 3 and 4 on the review. Okay, so we've already practiced that today. All right, so 14 and 15, these are derivatives before we knew the shortcuts, okay? So don't expect these were necessarily your favorite type of questions, but the process for finding derivative, okay, the formula for derivative is the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, that is our process always. So you can do the 4-step method. Remember, the 4-step method is just where you line out all the steps. Okay, so let me write down the equation. F of x equals -3x plus 2. So let's run through those steps. So we would have -3 times x plus h plus 2. Notice all I did there was plug x plus h into that equation. So I'm going to get -3x minus 3h plus 2. Okay. Step number 2 is to take what I got in step 1 and subtract off f of x. So I get negative 3x minus 3h plus 2 minus the original negative 3x plus 2. So if you work all of that out, you'll get negative 3x minus 3h plus 2 plus 3x minus 2, because remember this minus sign changes the sign of both things here. So these would go away, and so would the 2's. So notice you're just left with negative 3h. In step 3, you put what you got in step 2 over h. Okay, notice if we do that, we get negative 3. And so last but not least, this is the step I must see even if you don't show me all the other steps. So now let's do the whole thing. In other words, take what we just got and find the limit as h approaches 0 of that. So it's just going to be negative 3. Okay, this is the point where if you had an h, you would plug in h equals 0, but notice we don't have one. All right, so number 15 is more challenging, okay, but it's the same equation. G of x equals x squared plus 3. It's the same equation to find derivative. If I want derivative by definition, I do the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so let's just do the 4-step process. So f of x plus h, although this is technically g of h, or g of x plus h, so really all of these f's should actually be g's, but it's the same process. So we're going to plug in x plus h. Okay, remember what I said before, don't just square both of those. You're not allowed to distribute a squared in that way. You have to use FOIL here. So this would be x squared plus 2xh plus h squared plus 3 if you use FOIL and you simplify. So step number 2 is to take what you got in step 1, subtract off the original. So I got this for step 1. And I'm going to subtract off the original. Okay, so notice that's going to cancel these and these. Okay, leaving 2xh plus h squared. Step number 3 is to repeat what you got in step 2, but put it over h. So 2xh plus h squared over h. So notice there is an h in everything, right? So if we cancel that out, we get 2x plus h. And then last but not least, because this is actually the step that I must see, okay, step number 4 is to take what I just got and do the limit as h approaches 0 of that thing. So I'm going to put a star by this. Remember, this is the step I want to see for sure. So you're going to do the limit as h approaches 0 of 2x plus h. And then if I plug in 0 here, I'll just get 2x. Okay, remember, this is just finding derivative by definition. So we kind of already knew if we did our power rule what to expect for our answer. If you look back at what the problem was, right, the derivative of x squared plus 3 is 2x. So you can kind of already know what to expect, but again, you're going to have to make sure you could show it using all of the steps of the original definition that we used. All right, number 16, identify the values for which the function is differentiable. Use interval notation, okay? So in number 16, if it's a polynomial, much like whether it's continuous or not, it's just going to be differentiable for all. So I'm going to say for all x from negative infinity to infinity. Okay, but for 17, notice f of x as graphed in number 5, so I don't want to show that on screen anymore, but notice we were not differentiable at a. There was an asymptote at a, so I'm just going to say we were discontinuous at x equals a. And if you're discontinuous, then you are not differentiable either. So we're going to be differentiable for everything other than a. Okay. Notice all we did was kick out a. So because there's an asymptote at a, then we're not going to be differentiable either. We're not going to be able to find a derivative. If the function doesn't exist, we can't find a derivative either. All right, so these videos are a little more manageable in size. I'm going to stop this video and I'm going to start a second video for the second half of the review.